Good morning, I am José García Merino from the University of Extremadura, and I'm going to present this work, a surrogate model for the approximation of effective elastic properties of sphere-reinforced composite materials, which has been done in joint collaboration with Carmen Calvo Jurado from the University of Extremadura and Enrique García Macías from the University of Granada. In order to understand the motivation of the problem, I'd like to note that composite materials have great interest in material science. The study of average material properties of composites is called homogenization. There are several techniques to deal with homogenization problems, and one of the most popular ones is finite element analysis. Finite element analysis is a general numerical method to solve partial differential equations in 2 or 3 space variables. To solve a problem, finite element analysis subdivides a large system into smaller parts called elements. The problem is that carrying out a finite element analysis is computationally very heavy when we have a large number of heterogeneities. For this reason, we propose a surrogate model for the study of the influence of volume fraction and particle reinforcement radius in a sphere-reinforced composite material. For the material under study, we have selected epoxy for the metal matrix and glass for the particle reinforcement. The outline of this presentation will be the next. Once we have motivated the question, I'm going to state the problem. Then I will present our numerical results and finally the conclusions and proposals for future work. In a schematic way, our plans consist as follows. As we want to implement finite element model for homogenization, first we use MATLAB to develop the material microstructure geometry, and then pass it to ANSYS software. After that, we need to choose an appropriate mesh size for the model, and then we need to ensure that a model is large enough to be statistically representative. Once we have all, we only have to evaluate the model in a few points in order to construct the surrogate one. Generate a big 3D model of a whole material is an infeasible computational task. To deal with this problem, for our analysis, we will generate a representative volume element, that is, a small model which aims to characterize the whole structure. In our case, the RVE is a periodic 3D cubic cell with embedded spheres on it. The matrix material is epoxy, and the spheres are made of glass. In order to form this model, for a fixed radius, centers are generated through a random sequential absorption algorithm. It is important to note that a particle is allowed to cut cell surfaces, and that when it happens, symmetric particles are generated in order to preserve periodicity. Take notice, for example, of this particle in the bottom and this one in the top of the cubic cell. To carry out a finite element analysis, we have to mesh the previously generated geometry. A finer mesh provides better results, but at cost of higher computational time. We will have to select the most appropriate mesh size, taking this into account. And the same happens with the cubic cell size. Our RVE should be statistically isotropic, and that happens when the cubic cell is large enough. However, in a 3D model, increasing a little the size implies that computational times rise dramatically. With the RVE on the left, we can run our analysis in more or less half an hour. On the other hand, after increasing a little the edge size, the RVE on the right needs more than 2 hours to run the same analysis. An RVE greater than this one is in practice almost infeasible. The analysis will need more or less 10 or 12 hours to carry out. But as we will see later, this side is luckily fair enough. Now I'm going to briefly explain a little theory about surrogate models. First, consider a mathematical model M which maps a multidimensional input parameter space into a one-dimensional output space. Due to uncertainties in the input vector, x is considered a random variable with known probability distribution. A surrogate model is then a mathematical function which aims to emulate the original model but at lower computational cost. For this purpose, Kriging and polynomial cause expansion are metamodeling techniques widely used in the literature. In this work, we will use a combination of both approaches. For the development of a surrogate model, we need two sets of points sampled from the parameter space, called training set and validation set, respectively. Then, we have to evaluate the model M on set T and solve an optimization problem, depending on the technique used. And then, finally, we have to assess metamodel accuracy, evaluating N and our metamodel on set V, on validation set. I'm going to start with polynomial cause expansion technique. Given our mathematical model M, we can write the output variable y as an infinite series on this way, where alpha is a multi-index, a sub alpha are the coefficients of the expansion, and phi sub alpha are multivariate polynomials. That polynomials can be Legendre polynomials, Hermite polynomials, depending on the nature of the input variables x. For example, for uniform distribute input variables, Legendre polynomials are employed. The previous infinite series is an exact expression, but in practice only finite terms of it can be computed. So there exists so many schemes to select which terms we will compute at the end. The simplest one is to select all polynomials whose total degree is less or equal than 2, 3, 4, etc. But this solution is not so good for high-dimensional problems, where a great number of coefficients may be computed at the end. A possible improvement is to use hyperbolic truncation scheme, which selects only a few of the previous one. But this solution is not the best one, and in this work we will use least angle regression, which combined with the previous ones provides a very good term selection. Very briefly, least angle regression algorithm constructs a set of expansions incorporating an increasing number of basis polynomials in each step. Then the resulting sequence of index sets is used to construct different expansions, and then the best metamodel is selected by cross-validation procedure. The expansion coefficients A are obtained by minimizing the expectations of least squares given by this expression of here. We turn now to talk about Kriging. Kriging assumes that the response of a computational model is modeled by a Gaussian random process with two parts, T and C. C is a zero-mean Gaussian process, and depending on the nature of T, we can talk about simple, ordinary, and universal Kriging. Simple Kriging if T is a known constant value, ordinary Kriging if T is an unknown but constant value, and universal Kriging if T is a regression model like this one. To calibrate a Kriging model, we have to select an autocorrelation function which depends on nature of the zero-mean process. That function will depend on some hyperparameters theta, and the main challenge is to find the optimal theta. The optimal theta are obtained through solving one of the optimization problems. This one or this one. This one is from a maximum likelihood scheme, and this one is from a cross-validation scheme. The main strategies to solve that optimization problems are local algorithms based on gradient, which often get stuck in local minimum, or global algorithms like genetic algorithms. A genetic algorithm is used in this work to get our final metamodel. Our joint approach, polynomial cause-based Kriging, consists in select a polynomial cause expansion as a trend part of Kriging. This trend part captures global behavior of model M, and then Kriging approximates well local alterations. The model accuracy obtained by this approach is at least as good as the best metamodel construct using the two previous techniques. Now, we are going to present our results. The first one is the mesh convergence. We have said previously that a finer mesh leads to better results, but also to a greater computational cost. Then, for a fixed geometry, Young modulus has been calculated over different meshes. And we found that assuming the finest mesh, this one, as the real value, the fourth one, this one, presents difference with last one less than 0.5%. So we have selected that mesh size for next calculations. Regarding for the RVE size determination, we have followed the same strategy. We have generated different cells and we have calculated material isotropy by the quotient of the elastic tensor components. Finally, an RVE with 240 micrometers edge length has been selected. Finally, two polynomial cause expansion Kriging surrogate models have been constructed using 20 training points. One to approximate the Young modulus of the composite material, and the other one to approximate the Poisson coefficient. Independently, a set of 10 validation points was considered to prove metamodel accuracy, and as an error measures, the determination coefficient R2 and the normalized average absolute error has been taken into account to assess metamodel performance. In order to construct our metamodel, the two variables taken into account were, on the one hand, volume fraction of the inclusions, and on the other hand, glass particle radius. The numerical results of our metamodel shows a great performance of the approximation. The well-known determination coefficient R2 shows that almost all model uncertainty is explained by our input variables, especially in the case of Young modulus. The main interest of our work is that now we can evaluate the Young modulus and Poisson coefficient over a 30,000 grid with different input parameters values in a matter of seconds. Evaluate a single point solving finite element problem needs between 2 and 3 hours of computation, so the surrogate model has a great interest in situations where a huge number of simulations have to be done. Conclusions. A highly accurate surrogate model has been constructed using only 20 training points. Moreover, we have found that volume fractions of glass inclusions dominates elastic properties of the material in comparison with particle reinforcement size. We find interesting that this technique can be generalized integrating more sources of uncertainty, such as matrix and inclusions elastic properties, or taking into account, for example, the spatial distribution of particles. Hope you like it. Thank you very much for your attention.